for that are just over the state line into Utah. Fossil Butte National Monument is a great place to go looking for. Well, you can't collect in the state park, but you can get a permit, or you can look in the same age deposits. They're Eocene epoch age deposits from an enormous lake basin that used to be here in the region. And quite a few different types of fish have been preserved in those deposits. Okay, we're going to take a look at fossils today, and as mentioned, they can range in a variety of ages. This one on the top left is something, a 400 million year old sandstone that's got some fossil shells in it, and they look kind of like these little white, kind of butterfly looking deposits here. These are hard parts from marine organisms. They're called brachiopods. But you'll see this designation 400 MA or sometimes MYA, and it means million years or million years ago. And that's a designation for the ages of fossils once that's been determined. Here's an example on the right of some other fossils. This time you're looking at some leaves, and it's younger. This is about 300 million years old, and it's in a shale deposit. So that black and gray kind of matrix you see around the edges of these leaves that have been preserved, okay? And plants are interesting. Sometimes we get leaves, we get stems, we get, like berries almost, or nuts, and we get bark, we get the woody tissues of plants can be preserved. Here's one that's younger than the top two by another 100 million years, and this is a 200 million year old sandstone with a fossil skeleton of what looks like a mesosaur. It's an aquatic reptile. Not very big. This thing is about, a little bit bigger than the size of your hand with your fingers spread out. And you can see the detail of the skeleton here. Okay, these limbs that are used to move its body through the water, and you can see there's bones that have been preserved all the way up to the skeleton and the tail. And then this last picture here is just looking at, kind of a typical collection in a museum or in even our collection back in school. We've got drawers with things that are labeled fish fossils or vertebrate fossils or invertebrate fossils, and the best stuff should have labels, should tell us who collected it and what it is if it can be identified, and where it was collected and what the age is. All of that is useful information about the past. So let's take a look at the fossilization process. And how does an organism become a fossil? Well, this is an example here, and in this particular example is a dinosaur that happened to be walking along the beach. This is very similar to our dinosaur ridge over near Morrison, Colorado, if you're interested in this process. But we've got quite a few footprints over there, and here's showing the last few steps from this particular organism here, this dinosaur, and then they took their last breath and fell over and left those footprints in the mud, and then the dinosaur collapsed and died right there. Well, it doesn't take too long before the flesh starts to rot away. Okay, scavengers come and pick away at it, and it rots away and just leaves those hard, bony skeleton parts behind. In the next stage, it's showing, because it's a shoreline, that the sediment or the water level rises and brings new muds across the area and buries that fossil with these brown muds. And that may continue over a long period of time. And see what happens as you've got layers of sands and silt which have buried themselves over the top of this skeleton also. And then the last step is showing modern day erosion from the area, and if we look and scour away at that cliff, here's that footprint that was up in the upper picture, and here's the remains of that skeleton which is being uncovered by somebody down there by the Jeep. so it's now exposed. So this is a fairly lengthy process, and in the case of the dinosaurs, you've got, 150 million years between their death and when we've been looking at their skeletons now. Now, as far as preservation goes, there can be excellent preservation, or there can be lousy preservation of the remains of organisms. Here's an example of some nearly complete preservation of this baby mammoth. This mammoth was about 1 meter long, and this particular one was uncovered in Siberia, some 37,000 years old is the age of this fossil. And because it was found in Siberia, we've got essentially the complete organism here. Okay, it's just like fish out of your freezer. If you like to go fishing, first thing you do when you come home, if you don't cook them and eat them right away, you throw them in the freezer. Well, it keeps all that flesh from rotting. And here you've got part of the trunk, some of the ear, maybe a little bit of the tail. It looks like it's been broken off. But the skin's there, even the wrinkles on the skin, even some hair on the skin. So when something is frozen, it is exquisite preservation. And in other cases, we get great preservation from fossils that are dried out. Can you guys think of why that might be the case? Or what can be done in order to preserve fossils in dried climates, in arid climate? And I'll give you a hint. What did the ancient Egyptians do to their pharaohs before they put them into the pyramids? Yep, you got it. They're mummified. They'd embalm them and put salts and preservatives with them and wrap them up. And so it turns out that humid climate and water is really a breeding ground for bacteria, and that will eat away the flesh. And so if you're in dry climates, if you're in frozen conditions, you get excellent preservation. All right, another example of some excellent preservation of fossils, this time in either tar or in amber. And on the left, you're looking at a skeleton of a ground sloth. This was a slow-moving, pretty big beast of the Cenozoic. This particular one doesn't move real fast, and it got trapped in a tar pit in California. Perhaps some of you have visited this museum in the Los Angeles area called the Tar Pits, the La Brea Tar Pits. There have been saber-toothed cats and mammoths, woolly mammoths, ground sloths, and other organisms from the Cenozoic that have been pulled from the tar. So there's no real oxygen, I don't want to say oxygen, not a lot of bacteria that are living in these conditions, and so you get exquisite preservation of these bones. Here's an example of an insect, and this one is about 200 million years old. So that would put us in the age of some of the early dinosaurs in the early Mesozoic. And in this case, you've got the preservation of the entire insect. And we've seen this in many different ages through geologic time, where that sap will get onto the insects and preserve them. In fact, if you remind me at the end, I'll show you a little news article that was published in 2016 about some amber that was found in Myanmar in a flea market. And it had pieces of some dinosaur tail in it, including feathers on the tail. And so it's excellent preservation. All right, let's take a look at some other conditions for preservation. Really, the chances of getting preserved are improved if you've got a hard part of an organism. And in this picture, you're looking at these shells from what are called brachiopods. These are marine invertebrate organisms, so no vertebrae. They look like little clam shells. They're not really related, but they have the same kind of function in the ocean. They filter feed and they attach themselves to the seafloor. But you're seeing a lot of them on here, and the part of the organism that's preserved are the shells, the hard parts. And this is true of much of the fossil record. Things like shells are hard parts. Can you think of some other things besides shells that are hard parts that could be good candidates for a fossil? What else is a hard part on an organism besides a shell? You could type an answer on there if you could think of another part of a organism that might be. Okay, bones. Yep, absolutely. Bones are a good one, especially with the vertebrates. We find bones or bone fragments. What else? Corals. Absolutely, corals get preserved. Yep, corals are an invertebrate, but their entire structure can be preserved. So that's a hard part. Yep, coral teeth. Yep. Now, for example, if we think about sharks, what other hard parts do sharks have? And there's not much there because a shark is cartilage. So it's generally just the teeth that get preserved. We also get scales from fish. Those can be a hard part. So the fossil record is going to be really biased towards organisms that have hard parts. If you were to think about a jellyfish and the chances of a jellyfish being preserved as a fossil, that's going to be pretty tough because there's nothing hard in that organism. Or a worm. We don't find much evidence of worm organisms in the fossil record. We see their tubes and we see their burrows, but we don't find them very often because those are made of soft parts. There are exceptions, though. You should know that there are exceptions. Okay, it looks like Brant's got a note for you if you want to look at some fossil preservation when you get a few minutes here, including amber. So thank you for that note. Here's an example, another kind of preservation. This is called carbonized. So you can see the leaves that have been pressed into the shale here, and the carbon film around the details of those leaves. By the way, tropical fern fronds are something that we find here along the Front Range in Colorado. If you look in the Cretaceous age sandstones in the Laramie Formation in particular, you'll be able to find examples of these fronds. And they're telling us that we had a tropical condition at the time that they lived. Here's another important one, and I would say a pretty common one, called permineralization. And in this particular example now, you're looking at, well, it looks like a tree stump out there on the landscape. And if you were to go out there and try to lift that thing, you wouldn't be able to lift it. It's extremely heavy because there is no wood left. It's called petrified wood, but the wood is gone. And this tree died, and when it fell onto the ground, was later buried with sediment, just like the dinosaur example. But instead of having any bones, the groundwaters were full and saturated with mineral ions, and they got into the spaces of the woody tissue and basically filled them with minerals. And in this particular case, the detail is still preserved. Look at the exterior. You see the detail of this bark out here on the edges of this piece of, it's now stone, okay? If you wanted to know the age of this tree when it died, how could you figure that out, even though this is a stone now? Would there be a way to determine the age of this tree when it died? What could you try to do? By the way, these are examples. This one's from Arizona, and if you get a chance to go to the Painted Desert National Park in Arizona. It's worth a stop. We took students out there last summer to look at these things, and these trees, they're basically like redwood trees, and they are all over the landscape as far as you can see. And there's just tons of them. And a couple of you mentioned count the rings on there if you can see them. That's right. And we had some good exposure on some of these petrified wood examples. You go in there, look for the rings and start counting, and you could see how many are there. Sometimes you can see a lot of detail, and the color of the stone is quite spectacular. There's jasper and chalcedony and other kind of cherty like silica rich minerals. So very good. That's how you could figure out the age of the trees when they died. Now everything I've showed you up to this point is something called body fossils, because we've had some sort of remains of an organism. Those hard parts are telling us, you know, from the scale or the teeth or the bones, that there was a creature there. But there are other kind of fossils called trace fossils. And in this case, there is no body part. We are now looking at the evidence of activity. So something that the organism did was preserved in the rock, and there's no hard part left. So here's an example of that from the top view looking down. This is an example of some tracks, little footprints from some sort of a reptile that came along here, and it was holding its tail up in the air. Sometimes when you look at reptile trackways, you'll see a little line that runs in between the footprints as well, and you know that they were dragging their tail on the ground. This picture in the center is showing little footprints, but it's from the bottom side of the rock. So you can flip the rock upside down and see if they pushed their foot all the way through to the opposite side. And then this last example here is showing evidence of activity. Now notice there's the lens cap from a camera down at the bottom, okay, to get an idea of how big these features are. But across the rock you see all these little wiggles and swirls that are moving across. This is showing the trace of activity. These are what we call burrows. So there are a lot of organisms that burrow. Can you think of any that burrow in the sand? If I told you this was a sandstone, you'd go up there and feel it, and feel that it's gritty. Okay, so this rock is a sandstone. Can you think of any organisms that burrow or dwell in sand? Snakes? Okay, interesting. They can certainly make a hole. Crabs? Okay, Katie, thank you. So you're thinking marine realm. Spiders can dig their way, make little tunnels and nests down into the ground. Very good. So this particular one is probably the work of shrimp or clams or crabs or something near the ocean at a beach. If you've ever gone digging for crabs before, maybe you've played in the beach and you watch them dig down into that sand. And if they're looking for food or burrowing, they will leave these traces behind. And that tells us that there was an active biota that used to live in those rocks. And again, at Dinosaur Ridge, the ridge that's exposed to the basin there, to the valley, is just replete with burrows. They are all over in the sandstones, marking the shoreline. All right, not all fossils are the same size, and these are some examples of fossils that are very, very, very tiny. If you look at the scale bar down here, 40 microns, this is about the width of a piece of paper. Okay, so it's extremely on the edge of the piece of paper. It's like a human hair in diameter. Okay, so you see these little star-shaped deposits and these little platelets and fragments here. These are all plankton right here. These globigerinoid plankton. These perforated surfaces here and punctuated with all of these holes. Well, these are all showing the debris from the ocean. And so these are the skeletons from little microscale plankton and things that float in the ocean. And when they die, their little skeleton will sink down in through the seawater, and it will collect and make an ooze and eventually a rock called limestone, or a chert. And so these things are examples of fossils, but they're extremely small. And so with a microscope, we can use them to help understand the conditions of the ocean, which cover most of the planet. All right, let's look at a few other examples here. Extraordinary fossils because of their preservation. Now, I mentioned that hard parts are typically preserved, but in some cases we do get soft parts and tissues, and that's the case in this example here. You're looking at about half of the organism here from an old fossil mammal, and this thing is about 50 million years old. Based on age dating the rocks above and below it, we know that this is sandwiched within that particular age. And this one was collected from Germany in an oil shale, okay? And what they're highlighting here is the preservation of some of the skin. And I think you can see that wrapped around these hind limbs here up towards the pelvis and even onto their backside. There's some skin that's preserved. Well, let me ask you today, if you want your own skin on your hands, if it's really dry and cracked, what can you do in order to preserve your own skin? What can you do to keep it from cracking and drying and peeling off? What do you do to keep your skin healthy? And maybe you've in fact, I did this just this morning, to be honest. I was looking at my hand this morning and I was like, man, my knuckles are hurting. And I made a fist and my skin was just cracking across the top of my knuckles. And so I put something on them right away. Moisturize it, that's right. Put them in. That's right. Well, you put some oils on it. You put some sort of a lotion on it, right? And so this particular rock happens to have oil in it. That's this brown stain that you see across this particular rock type. And so that oil has worked as a moisturizer and a preservative for the skin of this early mammal. So if the conditions are right when they're buried, they can last a long time. But it is rare. Go to the spa. Okay, that sounds good. All right, here's another example of some great preservation of detail from what's considered the first birds in the fossil record. And the name of the first birds, scientifically, they're called Archaeopteryx, and they're about 150 million years old. So similar timeline to dinosaurs on land. There were other flying reptiles at the time, but we also find this in the fossil record. This particular fossil is from the Solnhofen limestone. This is in Germany. And if you look at the limb bones coming off the hind legs here, okay, you can follow the bones down here to the digits on the bottom of the skeleton, and then follow it wrap around on its vertebrae up here to his head and the beak. But notice on the forelimbs coming off kind of the shoulders and arms here, you've got 4 digits, and the longest ones, it looks like these have these impressions right into the rock. And you can see this all the way around on both sides. So this impression of what we think are some of the very first feathers that are connected with birds. And also look at the tail down through here off the tailbone. You can see there's an outline of some feathers that were pressed into the limestone in addition to the hard bony structure. So very extraordinary preservation. Other Archaeopteryx, Archaeopteryx have been found besides Germany. Maybe somebody can Google that. I'm pretty sure there are some that have been coming out of China in some of their deposits in the last couple of decades. We found several examples of Archaeopteryx and early birds there as well. Okay, just a couple more things to kind of wrap this up, and then we'll take a short little break when I'm done here in just a moment, and kind of just talk about what we've learned, and then we'll take a break and come back and look at this lab activity. And I think you'll benefit from seeing how to figure out the absolute ages. But just to kind of finish this off here, let me show you a couple of pictures here of some important fossils. And sometimes when we're identifying fossils, there are certain fossils we call index fossils, and those are particularly useful in certain time periods of the geologic past. And you're looking at several examples here. The first one on the top left, the trilobite, is an example of an invertebrate fossil that lived in the ocean but today is extinct. So this thing died out in the end of the Paleozoic, the Permian extinction, and has not been in any rocks younger than Permian, has not been found across the globe, but thrived and was really successful in Paleozoic times. Here's an example of another fossil called a gastropod, commonly known as a snail. Sometimes they're on the land, sometimes they're in lakes, sometimes they're in the water, in the oceans, and they can be useful too as far as finding what kind of environments these snails congregate and thrive. Here's an example of a bivalve, more typical of like today's clams. And I'll tell you, some of the clams from the Cretaceous section, it seems like to me when I think about the geologic past, like the Mesozoic and the Cretaceous in particular have some of the biggest fossils on Earth. The big ones like the dinosaurs, and the big ones like the ammonites, and the big ones like the clams. There's one group called the Inoceramids that lived in the Cretaceous oceans, and I've put my arms around these clams and I can't fit them in my arms. Okay, they're as big as car tires, just huge. Some of them have gone extinct, others survived and are present in today's oceans if you've gone shell collecting in the oceans. Brachiopods are another filter feeder, some of which survive in extinctions, others do not. Same thing with the bryozoans, they're sensitive, they're sea creatures. Here's one called a crinoid, and this is interesting. I'll draw a little picture, but I'm curious if anybody in the class has a saltwater tank. If they've got saltwater tanks that they watch or manage or have at your house. And in a saltwater tank, you know, you've got the little reef rock that you got going in there, maybe you got some coral in there and this little sponge growing in there and whatever, some little clams, a couple fish. Oh yeah, let's put the fish in there, swimming around in the water. Well, this is another creature that you can put into the fish tank today called a stock crinoid, but they can move. And so you see these little holdfast, they look like little legs on here. It's very important that you keep a lid on this particular saltwater tank, because if you don't and you have crinoids in there, they can pop off the lid and you'll go in the room later and you'll find them on the floor and they'll be dead because they crawled out of the tank. I had a student last semester who worked with saltwater tanks. It was kind of fun. He'd show me like the dental office or the mall or wherever these tanks were set up. He would manage the temperature and the pH and the salt levels and the nutrient levels and the light that was in that tank, and he did it all remotely off of his iPad, and basically would get notices from a certain tank. It says, hey, it's too cold, turn up the heat, or hey, it's too salty, turn the salt down, and would add little chemicals and things remotely to keep the saltwater tank healthy. I thought that was pretty interesting work. Very sensitive system, and they are in the oceans too. Here's an example. This is a graptolite. This is another example of an index fossil. Things that have gone extinct are good index fossils because they tell us the general age. This one is Paleozoic. Same thing with the graptolite. They do not live today, but they are Paleozoic. Ammonites were thriving in the Mesozoic. We have some descendants similar to these creatures called the chambered nautilus today in our oceans, but these ammonites with these complicated sutures are no longer present. But some of the best fossil deposits of these in the world are found just outside of Boulder, Colorado, in a designated preservation area. It's just amazing. Large creatures of the sea. Sometimes corals can be preserved. Someone mentioned that too. Okay, so we use fossils, and by the way, everything on this list here, you're looking at all of these, they have something in common. They're all from the sea. Well, maybe the exception of the gastropod could be a lake as well. And no backbone. Okay, what we call invertebrates. Inverts. Okay, so no backbone. The hard parts that will be preserved here are the shells and the fragments of these organisms. And this is what we see in the fossil record. For the first, almost 4 billion years of Earth history, things are pretty benign and pretty, they're absent of life as fossils in the rock record. But once we hit about 542 million years ago, we start to see all kinds of organisms occur in rocks around the Earth, particularly, in the marine rocks. And that's what's referred to in your book as the Cambrian explosion. Well, it's not an explosion like something blew up. This is an explosion of life, meaning before this point, there was virtually none. They were just simple-celled organisms, things we call prokaryotic organisms like bacteria and algae, and they're preserved in some rocks. But at the point of the Cambrian time period, now we've got eurypterids and sponges, and here's some trilobites down here, some echinoderms right here, early kind of crustacean-looking organisms here, more different kind of a trilobite in the background, and even some swimming arthropods you see in this cluster out here in the ocean, and all kinds of crinoids. That's this dark blue stuff that you see right there. So the oceans are filled with life, and there is a rapid evolution that takes place at this particular point in time. If you're interested in this stuff, by the way, I put a pitch out to take the next geology class, which is Geology 112. And in that class, in Geology 112, we examine the fossil record from the ancient up to today. It's the second part of this series. And start with the Cambrian explosion and work our way through all the Paleo, Meso, and Cenozoic life. And some students really like that, and you'd have good fundamentals if you've already taken this class. Okay, the last thing I want to finish up with here is just to talk quickly about extinctions. And on Earth, we have had several of them. And if you take a look here at this chart, there are 5 major extinctions, and see if you can find where the most significant ones have occurred. And if you look at the chart, you'll see on the left a count of the number of genera. Okay, so it's kind of like the number of species. Think of it as diversity and numbers of organisms here. Remember, in your biologic classification, your Linnaean classification, you've got kingdom, phylum, class, order, family, genus, and species. Well, the genus level is is a very small division on life, and so it represents a lot of diversity. And here you've got between 0 and up to 4,000 genera that have been identified. On the x-axis, you've got geologic time, and this is shown in millions of years. So notice if we worked our way from about 542 million years ago, that would be the beginning of our fossil record in the Cambrian, and then we'd work through the Ordovician, Silurian, Devonian, Mississippian, and Pennsylvanian are combined as Carboniferous, and then the Permian right here. So everything that's in the blue boxes are Paleozoic in age. The Paleozoic era, which has these several periods in it. And then everything that's in the green boxes, we're looking at the Triassic, Jurassic, and K for Cretaceous. These are Mesozoic in age. And then in orange over here on the right, at about 65 million years up to the present day, the Tertiary and Quaternary constitute Cenozoic age. And then we, of course, are at time 0, would be like right here on the edge of the line. Okay. So what we're looking at here, where are some of these big extinctions? And so you look at the counts of diversity here. It looks like I've got a note Katie's picked up KT as a major extinction. That's right there. So let's circle that one. That's where there was significant life that was blooming up to this point and then just fell off and took a dive. As far as the loss of life goes, this is considered the second worst extinction on the planet, but there's one that has been even more devastating. You see another one that's particularly bad on the life of the Earth. Or I should say, maybe bad's not the right word, but devastating. I hope that you can see, there's actually, they're pointing to 5 of them here, aren't they? Yeah, you got it, Daniel, right there. So let's just look at all of them. Here's one in the end of the Ordovician. Here's one at the end of the Devonian. Notice how life is climbing, boom, falls off. Life is climbing through the Ordovician, boom, falls off. Here it's kind of wiggling back and forth, but right here at the end of the Permian, right there, and it comes down and just falls off. This particular extinction is the big whopper for our planet. And at this point, we have essentially no life on land. So everything was living in the oceans. And of that biology, 95% of it goes extinct. So only a few things in the sea, a few clams and brachiopods, survive the Permian extinction. There's a rebound in evolution through the Mesozoic, and some of the fish and fish vertebrates, and then the cartilaginous fishes, they survive like sharks. They've still been around ever since the Paleozoic. But we also see an adaptation as things start to move onto land. And so not only do the oceans rebound in their numbers of organisms and diversity, but also things move onto the land. And this particular time is called the Age of the Reptiles. In green, all of these units. So reptiles dominate the landscape. There's also marine reptiles and aquatic reptiles in the oceans in addition to the other things. And they build up quite a number up to this point here at the end of the Cretaceous. And then boom, they fall right off here, and Katie mentioned that one as a nasty extinction. That's true. It's something like 75% of the life on land was lost. The dinosaurs being some of them. So the age of reptiles goes away, but that opens up a niche for a new group of organisms. And in the Cenozoic, look at the diversity that has taken off ever since that extinction at the end of the Cretaceous. today, what are the organisms, particularly on land, that dominate the landscape? What is that group? And by the way, you and I belong to that group. I'll give you a hint. It starts with an M. And it ends with an mammals. Yeah, I think I heard you yell it out, Matt. There you go. Thank you. Yeah, mammals. So we live in the age of mammals. That is the Cenozoic age. And mammals have dominated the Earth really since the KT mass extinction 65 million years ago. So some major extinction events, loss of a huge diversity of life. Okay, so let's just kind of summarize here. What do you guys see as some highlights for today? Can you share? And would love to hear your voices too, but you have to unmute your microphone. Just share with the class here, what are you picking up here as some of the main points for fossils, or things that you've learned about fossils today? Or you can type something, that's fine too.
So I wanted to ask, it's the first extinction, it's the Orodovician/T. What does that T represent on there? Because there isn't a, the next period is a Silurian.
I think it's a typo, to be honest.
So it should be an OS extinction?
Yeah, I think they made a typo right there, Dan.
Okay, cool. Yeah, no, I was reading about the KT boundary, and since K was taken for something else, or C was taken for something else, they used K because that's how they spell Cretaceous in German.
That's right, and the reason why they use K instead of a C is to avoid confusion with the Carboniferous in the Paleozoic, because in Europe, where much of the initial geology went on, there is no Mississippian and Pennsylvanian age deposits. They're hard to discriminate, and so that block of time is simply called the Carboniferous. And to avoid confusion with the Cretaceous, the letter K is used to represent it, and that's why it's the KT boundary. So great question there. Does that help?
Yeah, thank you.
That? Okay, good. All right, a couple of other comments here. What you've learned, ages of fossils. Yeah, and particularly the main groups here. Sandy, so you've picked up on some of the dominating groups in the Paleo, Meso, and Cenozoic, being the reptiles, the mammals in the oceans, the invertebrates, and again in the Geology 112 class, we look at these in much more detail and see which ones dominate different periods. There are index fossils for many of those periods of time. So let's see, Calvin asked a question about fossils. How can fossils make the oil? Well, this is a great question, and the oil is really generated from marine life. If you think of the tiny little microscopic organisms that live in the ocean today, our oceans are full of little marine organisms called plankton. And they look kind of like this debris here. And so Calvin, if we were to take these materials, if I was to draw, okay, a little picture, here's our ocean. Okay, so we're floating in the ocean here, so put a fish out here. And these are just little dots in the ocean. And when they die, they sink down all the way to the bottom, to the seafloor, and will start to accumulate a layer. And it takes zillions of these things, okay? But each one of them has a little bit of fatty lipid makeup in its organism. And so as that gets buried down into the earth deeper and deeper, it gets warmer, and eventually that little waxy lipid will get cooked out of the microscopic organism and make a little droplet of oil. And then that oil will move and migrate its way into some sort of a geologic structure, okay, like a little, think of it as a little hill underground, and that's where that oil will accumulate. And so later in time, if you wanted to prospect and look for that oil, that's the target that you'd want to come and drill into, is something like that. But it comes from just tons and tons of these little itty bitty tiny plankton that have a little bit of fatty material in their makeup. Sometimes people ask if the oil came from dinosaurs. Well, not the big dinosaurs that are the vertebrates you see on land, but they came from the same age. Think of it as dinosaur microfossils. Plankton from the sea tend to be the best source for the oil. And by the way, I'll talk a little bit more about that subject towards the end of the semester. I've got a presentation I'll share with you on that. Great question. Okay, that sound good? So let's go ahead, you guys. Let's go ahead and do this. Let's take a little break. Can we regroup at 4 p.m. is what my clock says on my computer here. That's like, what, 6 or 7 minutes? So I can just run downstairs and grab myself another drink of lemonade, and then come back up and we will look at the lab activity. I'll pull that up and walk you through that so you can get ready for that one, okay? If you've got any text conversation, go ahead and do it, but otherwise I'll just be back in a few minutes. Let's get that set up here real quick.
Okay, I don't know if anyone else is having this problem, but I just want to ask, like, all of you guys. Are you guys also having trouble accessing past meetings?
Did you say have trouble accessing the past, like this video here, like the recordings?
I still need to access the one from April 2nd because I still have not done that quiz thing that was due, and every time I click on it, it says video not this video could not be found.
Yeah. Yeah, I think that's been a lot of people. That's why. So I talked to him about it before. He doesn't know exactly why that is. I think I looked it up, and it just looks like since we're guests on the Microsoft thing, then we like don't have access to previous recordings. So I'm recording this session on my device right now, and I'll probably just put it on like YouTube or something like that, and then share it with you guys. But as far as the past recordings, I am not too sure how to access that yet. Is that what you're asking?
Yes.
Yeah. Unfortunately, I do not know how to access the past stuff, and he doesn't know either. I'll bring it up again to him. I think it's a Microsoft thing, but But you said you did not do, which quiz was it? The last quiz?
Let me find it real quick. I'm sorry.
Oh, no problem.
Yeah, the lab 9.
Oh, okay, the lab 9.
Yeah.
Okay. Yeah, I'll bring it up. I'll bring it up to him, and he can bring it up when he gets back too. Either one.
Yeah. He also said he was gonna email me the link via my student email, but I have that daily and there's nothing there. I don't know what's going on.
Yeah. Yeah, I think it's a Microsoft thing, so I'm not sure how to access the past stuff, but I'll start recording these sessions. And we'll see how that goes.
Okay, thank you.
Yeah.
Hey, Brett.
Yeah.
Will you be doing any type of studying for the next exam through camera?
Yeah, I'll do that. I looked because the next exam is in a week, so I don't know what days are good for everyone. Should I just do after? Should I do after next Tuesday, like after class?
That works for me. I mean, everyone's stuck inside.
Yeah, or should I do? I can do Wednesday, like the day before the exam.
Yeah, any day is fine, as long as we set a time everyone agrees on.
Sure.
Classes and going on. It'd be really cool. Just do it for all of us to get prepared for the test.
Yes. Yeah, I agree.
All right.
And does the Microsoft Teams work well for everyone? For you?
Yes.
Okay, cool. Yeah, let's briefly let's kind of roughly plan on next Wednesday, the day before the exam.
All right.
How's everyone else been doing, just in general, with this class, outside of the class?
It's been so hard adjusting, going from face to face to everything online. My time management, my motivation is just non-existent at the moment.
Yeah, it can be hard to reset up those routines for sure. For me, I've been just trying to as soon as I wake up, I don't know. Well, not I usually kind of sit outside or something, and then I'm like, all right, which class am I gonna do first? And I just sit down, do that class. But for me, it's hard just to sit in one spot with all those classes in one spot. So I gotta get up, do some push-ups or something, just something in between each class, kind of reset my brain.
Yeah, I've been that way as well. I decided to take 9 classes this semester.
Ooh.
So it's been a lot.
9 classes?
Yeah.
What the heck?
Yeah, it's a lot, but I have to give myself a schedule, and I think my important thing that I realize now is that I have to stick to my schedule, and if I have music one day, or I have criminal justice on a different day, I need to do it that day, and I can't save it for the next day because it's gonna get bad.
Yeah, I feel like it's almost easier to say, oh, wait till tomorrow. When everything's online, you just gotta do it.
Yeah, definitely.
Okay, we got. Get me back in the chair here. Okay. So the next thing we wanted to do here is just give you an overview of this lab activity. This is your last lab assignment for the semester, and I've just cut and pasted a picture of that lab exercise, and I want to talk you through some detail. What you'll want to do at the end, okay, what does Covey say? 7 habits of highly effective people. One of the habits is to begin with the end in mind. So with the end in mind, what you want to deliver back to me on D2L is this particular exercise, and you're going to explain an order of events and also share 3 calculations on how to determine the age of 3 igneous rocks in this picture. So that's what I want to walk you through so that you'll be comfortable putting that together. Okay, so when you open the exercise, when you have a little time, you'll open it up, you'll see it looks just like this. And again, these are the things that you're going to do. You can read through those. There's only 2 or 3 paragraphs, but you want to figure out the order of events. Okay, it's a cross section. It's kind of like you're looking at a canyon wall, and you want to figure out the order of events. There are 3 units. There are 2 units there which represent unconformities, which are erosional surfaces, letter C and letter H. I'll point those out. And then there's a procedure to follow in the lab book about the age calculations. I'll give you my understanding of it and show you how to do it my way, but you can also follow the lab procedure out of the book. It's fairly simple. And then something else to note in the cross-section is that there are 3 igneous rock units, letter L, letter D, and letter I. And it's as if those rock units were sampled. You go out and you break off a piece of them. They have a radioactive character to them, like we learned from the half-life calculation last time. And so we would sample those minerals and come up with an age based on an equation I will show you. Okay? We would measure those samples in the laboratory and get proportions of uranium and lead, or strontium and rubidium, or argon, or something else. So I would recommend you go back to the lab book if you get stuck on this activity and just review these principles if needed. These will help you sort out the order of events. Okay, the first is just a quick review here, the law of superposition. I think I showed you a little video out in the western part of the Colorado Plateau. We flew around in a plane, and we saw where some rocks were higher in the cliff and some were lower, and we understood this law of superposition. It just says that the layers on the bottom are oldest, okay, and the youngest layers are at the top, if you've got an undeformed stack of rock. The second is the law of original horizontality, and that means that the rocks would be deposited fairly flat, usually in ocean basins over a broad area. And if you find the rocks to be moved from a horizontal orientation, then that would have been a deformation that postdated original deposition. That's a mouthful. What am I saying? Rocks are laid down flat. If they're curved or bent, that happened more recently. The law of original lateral continuity means that these deposits cover a broad area, and canyons and rivers can form canyons and erode down into it, but they used to be continuous across those canyons, so we say they were laterally continuous. Cross-cutting relationships tells us that a fault that runs through a stack of rock is cutting through that particular stack, and therefore must be younger than the geology that's there. Or, in our case on this particular exercise, we've got igneous intrusions that make their way as dikes and sills into this geology, and so that geology must have been in place first before it was cross-cut by igneous activity. So you'll see those examples. The last one is inclusions. It's not important for this exercise, but it just tells us if you've got older rock incorporated into a unit, then the inclusions are older than the rock they're in. So you can, this is from the lab book, and you can refer back to this as you sort out the order. But let me get you started, because that's kind of step one of the process here. And if you read down through the instructions here, it'll say, let me make this a little bigger. Okay. Whoops, don't go there. It'll tell us that. There we go. The oldest rock unit in this canyon that you're looking at is letter G. Okay, I'm getting that from reading this paragraph right here at the bottom of the page. That's the oldest rock unit. And you see the trees up here on the landscape. It's like you've parked your car and you're looking at the road cut in I-70 as you leave Denver. It's just a tremendous exposure of all these layers and features in the side of the cliff. And so we're sorting out which one's older and which one's younger. And in this case, we could look at letter G. We could say that letter N is actually younger than letter G. Letter B is younger than letter N, and so forth, all the way up through this column of rock. Why? Because G, N, B, S, F, O, J, they're in a stack. And so we know, since G is the oldest, superposition would tell us these others are younger than G. And we'd work our way up until this point, letter H. And from the instructions up above, it says that letter C, right here, and letter H are unconformity surfaces. That means those are surfaces where there was erosion. And I wish that when Uwe put this lab book together, that he would have used a wavy line. Okay, there's an arrow right here by letter H, and it's pointing to this contact, that surface that runs along the length of the picture. Okay, so all the way up to letter Q was deposited, and then erosion came to the area. Actually, up to letter Q, then it was deformed out of horizontal. Then we've got letter H, which eroded the area off almost flat, and we had new deposition come. Letter E, letter P, and letter R. And then notice we've got a feature here, letter D, which is cross-cutting through E, P, and R. So letter D must be younger than the stuff it cuts. It must be younger than letter R. You can sort out what to do with letter M, and then letter C is another surface of erosion. Okay, so to this point, now the area gets planed off by erosion again. Then superposition is putting A on the bottom, followed by unit K, and then notice that letter I is cross-cutting through this entire stack again. So letter I must be the youngest feature on this exposure. And so that's what I've drawn down here, giving you a start. It says letter G is the oldest, followed by N, followed by B, and then you sort out what's in between. Letter I is the most recent. Okay, so that will be part one of this lab. I want you to give me that list of letters that shows me the order of events from this picture. Okay, now let's look at the second part of this lab in determining the age. There is a, sure, let me fit this back in here real quick. Bear with me to fit this back on view. Okay, so there is in the lab book also a mathematics solution to actually calculate the age of those three igneous rock intrusions. And the equation that we want to use is right here, okay, where it says letter T is equal to T sub HL over 0.693 times the natural log of capital P over P naught. And you can read a little bit of detail about that. I will explain it to you in just a second. But what we're going to do here is sample the rock from those igneous units, measure it in the laboratory to see what are the proportions of radioactive parent and daughter product, and plug it into this equation in order to calculate an age. One of the details you're going to need is the half-life value depending on which isotopes are in the rock. So we've got both parent and daughter isotopes, which are given in the paragraph on the first page, and I'll show that to you again. But here's where you will go if you're dealing with potassium and argon. Okay, it's got a half-life of 1.25 times 10 to the 9th years. These are the kind of igneous rocks that might have things like potassium feldspar, muscovite, hornblende. These are minerals that you have touched in class and that make up the constituent minerals of granites, for example. Other igneous rocks might have some combination of uranium and lead. Here's uranium-238. Here's uranium-235. Uranium goes through a multi-step decay, and so you might have a stable lead value at 206 or 207. Depending on which one you're dealing with, you'd use different values in the half-life term. The other one that you'll use today is rubidium and strontium, okay, 87. And it has a half-life value of 48.8 times 10 to the 9th. These are potassium-bearing minerals, felsic igneous rocks. So this chart is coming from the lab book. Okay, so you'll want to make sure you get access to that and have it handy when you make your calculation. All right, so let me go to the assignment now and let's set up a problem and we'll actually work an example together. Okay, so here's the first paragraph on the lab activity, and it's going to describe what information we've got. We already mentioned in the relative age assignments, letter C and letter H were unconformity erosional surfaces. That's fine. But what we're doing now is we're looking at the 3 igneous intrusions. Letter D is a mafic igneous intrusion, and it tells us what parent and daughter isotopes are present in the minerals of that igneous intrusion. 5.20 moles of potassium-40 and 0.45 moles of argon-40. So the potassium is the parent and the argon is the stable daughter product. So let's go ahead and set up this particular problem, because that's the first of the 3. We want that equation, which is, I rewrote it here. T is equal to T sub HL over 0.693 times the natural log of the quotient of parent to the sum of parent and daughter. Let me label those terms. So T, which is time, this is going to calculate the geologic age. That's what we're interested in at the end of the calculation. The T sub HL, that's the half-life isotope value. We get that from the chart that I just showed you. Ln, this is a feature on your calculator, so you'll push the Ln button in order to get this result. The P value here is the number of moles of the parent isotope, and then the P naught value in the denominator is the sum of both the parent and the daughter together. Because remember, those 2 isotopes together have to constitute 100% of the mass. So let's go ahead and let's see how we would move next. We've got our equation. We'd go to the chart, and in this case, remember letter D, it says we're looking at 5.20 moles of potassium-40 and 0.45 moles of argon-40, so we're going to use this top line value and this half-life term, 1.25 times 10 to the 9th years. So let's go ahead and we'll plug that into our equation here. We'll write it down. Okay, so here's for letter D, 5.20 moles of potassium-40, 0.45 moles of, whoops, I made a mistake, that's argon, right there. Okay, and we need both of those in order to make the calculation. Let's go ahead and we'll fill in each term. So here's our equation now, and we'll start to fill in the terms. T, which is the geologic age, 1.25 times 10 to the 9th. That's this term off of the chart. We've got the decay constant value there, 0.693 in the denominator. And then we're going to multiply by the natural log of the parent moles in the numerator. That's 5.20. Comes from here. And 5.65 is the sum of both parent and daughter. So if we sum these together, we get 5.65 as the sum. That's what's in the denominator over here on this side of our equation. So we'll take those values now, and let's go ahead and multiply some of those terms out. 1.25 times 10 to the 9th. Okay, that's nine digits after the 1 here in our scientific notation. So here we go, 1, 2, 3, 4, 5, 6, 7, 8, 9 spots after 1. And that's our numerator term. Here's 0.693. And then I've already calculated the division here. 5.2 divided by 5.65 gives us this lengthy number. And now we have the terms. We can punch those into the calculator, and I get a number like this. Okay, negative 150,399,727, depending on how many digits you round off here on the term with the moles value. By the way, moles is, remember that from chemistry, to give us equal proportions here and to keep the weights common. When you have moles divided by moles, that'll go to 1. So this will be a unitless answer, but it will be a negative answer. And that's what we want. Why? Because we are going back in time. We are finding an age. So the time value is negative because it's telling us years before the present or years ago. So I have just taken the final answer here, negative 150 million and change. I rounded it off, negative 150 million years ago, and that puts us in the Mesozoic. Okay, so that is how we can set up the problem in order to calculate that, and it's just a couple of punches on the calculator. I did a screen capture here when I just did it on the computer calculator a little while ago, but let me show you this as well, because you can run this off your laptop or your phone if you've got a scientific calculator on your phone. The first thing I did here is I actually did the mole term over there. Whoops, come here. There we go. 5.2 divided by 5.65, that's what I did first. In my calculator, it gave me this answer, 0.2920. I took that answer and then I pushed the natural log function of it. Okay, there's the ln function, and the natural log function on your calculator looks like this button there, ln. And then hit the multiply button, and we multiplied that by, remember, the half-life value in the numerator and the decay constant in the denominator, and put those together in our order of operations and pushed enter, and this was the value that I came up with. Okay, so negative 149,705,843, because on the computer here, because I can run out so many digits beyond the decimal, the value's just a little bit different than what I just showed you. So I rounded off a negative 150 million years ago. Okay, so that was the answer I just showed. Just like that. So I've just talked through a long explanation, but the punching of the buttons is really just a matter of a few seconds. Okay, but I want you to see how the organization goes. So let me just jump ahead to the end here, and then we'll see if there's some questions. So this is what you're going to turn into D2L. Okay, you want to turn in the page here that shows the order of events from oldest to youngest, and remember letter G is the oldest, and then it's going to go all the way up to letter I being the youngest in the relative ages, and then also show the 3 calculations, one for letter L, okay, and those details are provided up in this paragraph here. Letter D, which we just did, okay, it's another example, are also included in this paragraph, and then also letter I, right there, okay, which would be the 3rd igneous intrusion, and include those calculations. So you can put those all on a page, or this page, however you can show your work, and just put that all on D2L, and just drop that, either a picture or the file in Lab 10. And it should be accessible now. It says it's due today, but you can work on it today, and I will continue to take it for another week or so. If you need some extra time, that's fine. Even longer than that if you had to. Just communicate with me if you needed some extra time. But I wanted you to see how the process goes to work on this. Okay, so let me go back here to the chat box and see other questions here. Do you feel comfortable like you could proceed with this activity? Shrink that over a little bit. We'll see, or any other questions for today or for the class? I'm going to go ahead and stop the recording at the moment, but I'm just going to hang on the line here for a few minutes and see if you've got any additional questions or concerns. Okay, Romy. Yeah, you can fill it right in on a document or just take a picture. Either way is fine. I just want to see your order of events and see your calculations for this lab.
I have just a general question regarding Lab 9. I still do not have access to the meeting that was done that day. I was wondering what I need to do, or...
Let's see, what was Lab 9? Oh, that was the half-life calculation, I believe.
Yeah.
Have others found that? Who am I talking to? Who's asking that?
Geraldi. Sorry, I emailed
Geraldi,
you
okay.
everything and...
Okay, so Lab 9, there may have been, oh, I remember this one now. Yeah, guess what? You guys are one of many groups that are using this same software, and I found out actually through the Metro faculty that the day we did that lab, there was a kind of a surge in the Microsoft Teams organization because of heavy use. And there may have been some glitches and even deletion of files and some other things that happened on that day. It was not just our class. And so if you want to walk through any of that again, I'd be happy to do so. We can set up a time and I can show you how to do that.
Oh, okay.
You can still turn it in. That's no problem. Let's see. So maybe just hang on the line for a second here when we disconnect, Geraldi, and we'll figure that out.
Okay.
Calvin, you've got a question here. You just put the order of the letters and do the 3 calculations. Yes. That is correct. That's what I'm looking for. That looks good. Okay, other questions? In fact, Gerald, do you want to do that now?
Yeah.
Okay. We can close this call, and then I'll just have you reconnect, or if anybody else is interested, and I can show you how to do that on the half-life decay chart. You want to see an example of how to do that, so you can answer the questions. Okay, so let me just type here. Have a great day, everybody. If that's good, then go ahead and proceed. That'll be the last lab assignment for the semester, and you've got this detail on fossils from today, so I think you should be set. And then of course, if you've got any other follow-up, you can send me a note through D2L or whatever, and I'll see if I can help you there. Brent, are you still on the line?
Yes, I am.
Do you have any other comments or anything you want to mention before people go?
Not that I know of. Again, yeah, feel free to reach out to me if need be. And again, yeah, I recorded this session, so I will try and post it too if you can't access this one. And I'll try and send out the link to everyone.
Okay. There's a note here. Nora says you can't write on it. It's a PDF. So you could either print and write on it, or you could just copy it onto a document and draw on it, if you want to do it that way. Or if you want to just make your own, Word document, that's fine, and just say, order of events, and just list out the names, and then show your calculations that way. That would be fine. I'm flexible on how you deliver that back to me. Yeah, there you go, Nora. That's fine. Okay, you guys. Well, I have to tell you, this is not ideal. I would much rather do this in person, working on the whiteboard and see your smiling faces and all of that, but at least we don't have to breathe on each other, and we'll get this figured out. We don't have a lot of class left. We've got another test coming up pretty quick, and then we'll be really towards the just a few more lectures, I think, for the semester. So we are winding down fast. All right, I'm going to go ahead and disconnect, and then Geraldi or whoever else is interested, I will just reconnect on the same channel. Just give me like 3 minutes. I'll just reconnect back on the same channel, and I'll pull up the workflow for your previous lab.
Okay, I'll do that too.
All right.